In this video, I wanted to show you how you could use factorials in the combination formula to address problems like this example. How many possible 5-card hands of poker could be selected from a standard 52-card deck? So to remember, when we're asking to find the number of possible hands and you're playing a game like poker, the order in which you receive your hand of cards in your hand actually doesn't matter. It doesn't matter if I get a king, queen, jack, in that order, or if I get a jack, queen, king, as long as they're in my hand. So since order doesn't matter, this is a combination. So whenever order doesn't matter, and we're wondering how many ways can I select R items from a group of n, so a subgroup, order doesn't matter, and you're choosing a subgroup, kind of like when we're choosing a committee, right? This is what we call a combination. And in order to calculate combination, we could use the formula NCR, which says take n factorial over n minus r factorial times r factorial. And you can put that at the end or at the beginning. And so in this case, we're talking about a total n of 52. So we would have here 52 combination r, our subgroup size, is R. So in this case, our subgroups are size 5. R is always smaller than n. And to begin the formula, you would take 52 factorial, divide by R factorial, which in this case is 5 factorial, times n minus R factorial. Well, 52 minus 5 is what? If you said 47, you're correct. So that's the number that goes here, 47 factorial. Now, this is the part where if you were to put this in your calculator, you would have to do so very carefully and recognize that 52 factorial is going to be a huge number, because in reality, that's 52 times 51 times 50 times 49 times 48 times 47, technically times 46, 45, 43, all the way down until you reach 1. But I'm going to stop at 47 factorial. Think about why I'm doing that. I look below and I see I have 47 factorial, don't I? So if I notice that if I stop at 47 factorial, that means 47 all the way down to 1, and so does this. So technically, if I have 47 factorial on the top and bottom, what do you think is going to happen to this result and this result? They'll cancel, that's correct. 47 times 46 times 45 is on the top and the bottom. They'll completely cancel down to 1. All that remains then is just 5 factorial, which is 5 times 4 times 3 times 2 times 1. Now most students, I will say most students, if they have access to a calculator, right now they're going to do 52 times 51 times 50 times 49 times 48. And what they will get in their numerator is 311,875,200. Or in math, we would call that 300, sorry about that ugly one. We would say 311,875,200 for the numerator, divided by the denominator. 5 times 4 is 20, times 6 is 120. And what we would end up with is a division now. And we would divide these two numbers to get our final answer, which should be 2,598,960. So 2,500,000, sorry about that, my board got a little confused here. 2,598,000 and 900. Looked at my calculator wrong. 960. So this would be the number of possible poker hands. So that's how most students would probably calculate it. However, sometimes you'll notice professors and people who've done a lot of these problems will tend to do shortcuts. And so one of the shortcuts that I like to do, especially if I don't have access to a calculator in front of me, is when I get to this step here and I notice that I have some cancellation possible, like the 47 factorials, I think to myself, is there a way that I could cancel a little bit more? For example, I notice that here I have the number 5 in the denominator. Does 5 go into any of the numbers up here in the numerator nicely? Well, you might say, sure, Professor, 5 goes into 50. I know that. Well, how many times? 5 goes into itself 1 time, but it goes into 50 10 times, right? 5 times 10 is 50. Okay, so you can cancel, and now you have smaller numbers to multiply in the numerator and the denominator. And similarly, I could say, look at this number 4 here. Does this number 4 go into any of the numbers on top? Well, you might see 4 goes into 48, which is definitely correct. 4 does go into 4 does go into 48. You could have also done 4 into 52 if you preferred. If you did 4 into 48, you'd say 4 goes into itself 1 time, evenly, and it goes into 48 12 times, doesn't it? So it goes in there 12 times. And now I have smaller numbers up here. Again, this is still multiplication, isn't it? Okay, is there anything else that we can see that might reduce to make our life a little easier instead of using a calculator if we didn't have one? Well, I could look at 3 in the denominator and ask myself, does 3 go in nicely into any of the numbers on top? Does 3 go into 52, 51, 10, 47, or 12? Well, there's a little trick. It's called a divisibility rule, and it says that if you add up the digits of any number and that new number that you got when you added the digits is divisible by 3, then it turns out the whole number is divisible by 3. 5 plus 2 is 7, so that's not divisible by 3. But 5 plus 1 is 6, that's divisible by 3. So it turns out 51 is divisible by 3. You can check it out. It goes in how many times? Well, 3 goes into 5 one time, with a remainder of 2. And now I would have 21. 3 times 7 is 21. So it looks like 3 times 17 should be 51. And you can double check that if you don't believe me. So now I've replaced 51 with 17, 50 with 10, 48 with 12, and now 3 is replaced with 1 because I've done some division. There's a couple more numbers in the denominator to check out, namely the number 2, because 2 times 1, we know that's just 2, right? So does 2 go in evenly to 52, 17, 10, 49, or 12? Well, it goes in evenly to any even number, right? So how about we take the big one, 52. How many times does 2 times 1 is 2, go into 52? If you said 26, you'd be correct. So now notice what's in the denominator. 1 times 1 times 1 times 1. In other words, my denominator is just a 1. What's in my numerator? It should just be 26 times 17 times 10 times 12. Now again, you didn't have to do it exactly the way I did, but that's a little bit easier to work with. I could then multiply 26 times 17, and let's see what I get. 26 times 17 gives me 442, and I can see easily that 10 times 12 is 120. So let's go ahead and multiply 442 times 120. And I get, which number here? So that's 26 times 17 times 12. Oh, I see I forgot something. That's scary. Watch out for yourself, like a professor just did. There was a 49 I forgot to bring down here as well. So times 49, that makes more sense. So multiply that number I got here, these two together, was 53,040. 53040. Times 49, let's see what happens. There it is. I'm getting this answer. 598,960. So if that was confusing to you, don't worry about it. You don't have to do it that way your professor does. The only reason that's beneficial is because if you don't have a calculator sometimes, it's easier to simplify first so you have smaller numbers to deal with if you're doing mental math or doing math by hand. So I hope that helped clarify how you can use the combination formula to address a problem involving picking subgroups where order doesn't matter, such as a card of poker hands. Anyway, if you have any questions, feel free to email me and I'll be happy to get back to you. Otherwise, happy practicing, because remember, math is not a spectator sport. I'll see you next time.